first of all, this should be glued in on page 94 in your composition notebook. So if you don't have it on page 94, that is where it needs to be. But I wanted to review the wave book with you through this screencast and to help clear up any misconceptions in the concepts that we've had. What is a wave? A wave is a disturbance that travels through space or matter with a transfer of energy. And just so you know, in case you don't notice, the highlighted words are the ones where there are blanks on the book that you had to fill in. So pay attention to the highlighted words, especially comparing them to what you have on your book already. And as far as what is a wave, it is a disturbance that travels through space or matter with a transfer of energy. And remember that waves transfer energy, not matter. So energy is transferred from one location to the other, not the matter or the medium. There are two types of wave. One type is a mechanical wave, and a mechanical wave can be longitudinal or transverse. The other type of wave is an electromagnetic wave, which kind of refers to the electromagnetic spectrum. And on that electromagnetic spectrum, you have things like radio waves, microwaves, satellite waves, visible light is up there, infrared, ultraviolet rays, gamma rays. So those kind of rays or waves are on your electromagnetic spectrum. But electromagnetic waves are transverse waves. A mechanical wave can be transverse or longitudinal, as I've already stated, and they need a medium to travel through. So without a medium, you can't have a mechanical wave. You have to have a medium in order for the wave to be a mechanical wave, because it has to travel through a medium. Their movement can be longitudinal or transverse. Longitudinal waves are or can be called compression waves, because with longitudinal waves you create compressions and rarefactions. Compressions are where, like when we talked about the slinky would be bunched up, coiled up, or and rarefactions would be where the slinky would be spaced far apart. They are back and forth in motion. So like in class when we were pulling each other toward and pushing each other away from, pulling toward and pushing away from each other, we were demonstrating a longitudinal wave. Examples of longitudinal waves are sound waves, and they have that to and fro or back and forth motion. Transverse waves right here, the motion of the medium is perpendicular to the motion of the wave. Up here in transverse wave, that motion is parallel. So the motion of the medium is parallel to the motion of the wave for longitudinal or compression waves. For transverse wave, the motion of the medium is perpendicular to the motion of the wave. And that means that you will have an up-down kind of motion when you have a transverse wave, creating crests, which are the high points on a wave, or troughs, which are the lowest points on the wave, and it's discussed later on in this booklet. But you have your up-down motion with a transverse wave, and examples of transverse waves are light waves, waves on a rope, like in the video we watched with the little boy jerking the rope. It was tied to the tree and he had the other end and he was jerking the rope up and down, creating transverse waves. Standing wave or ocean wave. Also, we talked about a stadium wave being a transverse wave. If the people have to stand up and sit down, that will create a transverse wave. But it can also create a longitudinal wave if the people just sway from side to side instead of standing up and sitting down. If they just move from left to right or right to left, they could create a longitudinal stadium wave. Parts of a longitudinal wave would be compressions and rarefactions, and the compressions would be this part of the wave where the coils are bunched together or close together, and the rarefaction part of the wave would be this part of the wave where their coils are spread far apart or apart. Types of mechanical waves, how you can tell them apart. All mechanical waves are not the same. For example, light waves are a different type of wave from sound waves. So light waves would be transverse waves. Sound waves are longitudinal waves because the sound, the vibrations make the molecules bump into each other, creating compressions, and then they bounce back to their original position. So they kind of bump into each other and have that back and forth motion going on, like in a longitudinal wave. So sound waves are longitudinal waves. Light waves are transverse waves. Although they both transfer energy through a medium, which makes them mechanical, light and sound waves are mechanical waves. It's just that, or can be mechanical waves. Um, they both transfer energy through a medium. The movement of the wave through the medium is very different. And actually, I need to change this to ocean waves probably to make it more accurate, because ocean waves are mechanical waves. Light waves are actually electromagnetic waves. So let me make that change really quickly. So scratch what I said about light waves. Light waves are transverse waves, but they are electromagnetic transverse waves, and electromagnetic waves can only be transverse. But ocean waves would be a mechanical wave that is transverse, and different from a mechanical sound wave, which would be longitudinal. The ocean waves have that up and down crest and trough motion, like crest, trough, crest, trough. So ocean waves will be more of a transverse mechanical wave. Light waves are transverse waves, but they are electromagnetic because they do not need a medium to travel through. They travel through a vacuum. The motion of the medium compared to the movement of the wave can be classified as either transverse or longitudinal. So depending on if it's that up, down, or back and forth motion, is how you can classify waves as either transverse or longitudinal. An electromagnetic wave can only be a transverse wave, and it does not or do not need a medium to travel. So electromagnetic, like as in a light wave, they don't need a medium to travel through. They can travel through space. Outer space, you can still see light, but in outer space, you can't hear sound, because sound is a mechanical wave that needs to travel through a medium in order for the sound to be received to the eardrum, because it has to vibrate the eardrum so that it can be heard. But an electromagnetic wave, such as a light wave, does not need a medium to travel through. It can travel through outer space. We still can see light in outer space. That picture that would be right here that's not in this book would be an example of a light wave. And so that's why I put light wave right here, because that picture would be an example of a light wave. Now the parts of a transverse wave, which this is an example of a transverse wave right here. The crest will be the highest point on the wave, which would be up here. The trough will be the lowest point of the wave, which would be down here. The amplitude is the height of the wave, and it's also known as the volume of the wave. And the amplitude could be measured two different ways. You can go from the line of equilibrium, which is right here, to the crest, or you can go from the line of equilibrium to the trough, because they should be the same distance or the same height. From here to here should be the same height as from here to here. So you can either measure the amplitude from the equilibrium line up to the highest point of the wave, or from the line of equilibrium down to the lowest point of the wave, which would be the trough or the crest. The wavelength is the distance from one wave trough to another trough, or from one crest to another crest. So the distance from this crest to this crest will be this wavelength, this wave's wavelength, or the distance from this trough to this trough could also be symbolized as the wavelength. The wavelength is symbolized by this funky little symbol that looks like a upside down V that I drew on the board. So just know when you see that symbol that it symbolizes wavelength. The The frequency is the number of complete cycles in 1 second. So say for example you chose this line as the line that was your point, your beginning point, and you wanted to see how many waves pass this line in a second. That will be considered your frequency. The period is the inverse of the frequency, or the reciprocal of the frequency. So if the frequency is 5, then the period is 1/5. If the frequency is 2/5, then the period is 5/2. They are reciprocals of one another. The frequency is also measured in hertz, which is represented by the letters capital H, lowercase z, and the frequency is also called the pitch of a wave. I just wanted to point out that this little symbol right here is the symbol that represents wavelength. So if you ever see the symbol, and when we're talking about velocity, it symbolizes wavelength.